Right, good morning Year 12. So we're going to move on to the second part of the haloalkanes topic. We're going to look at formation of haloalkanes, so carrying out reactions with the aim of producing a haloalkane at the end of it. Now, this part of the topic introduces the first organic reaction mechanism that you're going to encounter during your A-level course. Now, reaction mechanisms are a step-by-step process to show how do you take molecules at the beginning of a reaction and turn them into the products which are made at the end of the reaction. So by the end of your A-level, you'll probably end up having to do maybe 12, 13, 14 different organic mechanisms to show the step-by-step process of turning reactants into products. And we're going to look at the first one today. It's called a free radical substitution mechanism. All the notes are here. So page 4, page 5, and just going down onto page 6 as well. Now I'm going to explain all these on a piece of paper so you can follow. You'll also need a spare piece of paper for yourself because I'm going to set you some tasks to have a go at during the course of this video. And then that will hopefully give you the knowledge and skill that you need to be able to complete some of the tasks from your question pack. Right, Year 12, so we're going to go through the free radical substitution mechanism. I'm going to go through two worked examples and hopefully I'll go through them slow enough so you can pick them up. Of course, you can always rewind the video and recap various bits if you need. And then I'm going to set you a couple of examples to have a go at as well. Okay, so I'm going to do the free radical substitution reaction between chlorine and methane. Okay, you always have to have a halogen, you always have to have an alkane. So in this example, chlorine and methane is what I'm using. Now, the initiation step is defined as the step which produces the radical. Okay, and in the initiation step, our halogen, so in this case, our chlorine, is exposed to UV light. Okay, now UV light is high energy light and it provides enough energy to break our chlorine to chlorine covalent bond, and it forms two chlorine free radicals. Now let me explain by what I mean by this. I'm just going to jot this down on this side here. Now, a chlorine diatomic molecule is a chlorine with a covalent bond between the two. And you should hopefully remember that a covalent bond is a shared pair of electrons. So I'm going to sort of represent that as a little dot and a cross. Now, what the UV light does is it provides the energy to break that bond, and essentially one of the electrons will go back to one of the chlorines where it came from, and the other electron will go to the second chlorine where that one came from. So that's why we end up with two chlorine radicals, and that dot there represents an unpaired electron. That's what makes this a radical. And hopefully you recall back from GCSE that all atoms are most stable with a full outer shell. These two chlorines do not have a full outer shell. They have an unpaired electron on their outer shell. That makes them highly reactive, and that's why as soon as free radicals are generated in this initiation step, that the rest of this reaction then continues. Okay, so in an exam, this is the only bit you need to write down. That's just my extra bit of explanation there. Right, the propagation step. Now, the definition of a propagation step is these are reactions which prolong the life of the radical. And this is where our methane gets involved. So there are two propagation steps. In the first one, our chlorine radical that we've generated up here collides with our methane. And what this does is it takes a hydrogen off our alkane. So it doesn't matter what the alkane is, the chlorine will always take a hydrogen off it. So if the chlorine removes one of these hydrogens, it's going to form HCl. And then because our CH4 has had a hydrogen removed, that's now left as a CH3 radical. So essentially the highly reactive species was the chlorine, but at the end of this step, it's now a methyl radical. Now there's a second propagation step because the methyl radical that we've just made then collides with some chlorine, a Cl2 molecule. Now if we look at the chlorine back up here, right at the beginning in the initiation step, lots of our Cl2 molecules will have split up into chlorine radicals. but not all of them. Some of these chlorines will have stayed intact. So that is where this comes from, a Cl2 molecule which hasn't been split up. Our methyl radical collides with this, and the methyl radical causes these two chlorines to split up. So one of them is going to stick onto the methyl, so we end up with CH3Cl, and the other one is a chlorine radical. One of those chlorines is left as a chlorine radical at the end of that process. So during our propagation step, we've actually made the haloalkane product that we were looking for. The whole point of doing a free radical substitution mechanism is to produce a haloalkane, so we've done that. Now, our dilemma now is this reaction is just going to keep on going because there's these highly reactive species floating around in our reaction mixture. These are going to keep on moving around and reacting until they no longer are radicals anymore. And that's what our termination steps are. The termination step is a step which ends the life of a radical. And there's three possible combinations that can occur here. So it could be that one of our chlorine radicals collides with another chlorine radical and they just pair back up again to reform Cl2, essentially the reverse of our initiation step. Okay? It could be that a chlorine radical collides with a methyl radical. So one of our methyl radicals from up there, for example, if they pair up together, that's going to make chloromethane. And again, that's a good thing. We want to make chloromethane because that's the aim of this reaction. Or it could also be that a methyl radical could collide with another methyl radical and we end up making ethane, C2H6. Now, that's not the end of the world, but it's not what we wanted. We didn't carry out this reaction process in order to produce ethane. We wanted to make in this case, chloromethane. So this is quite a good reaction because we end up with some of our product, but it's not the best type of reaction because we end up with some unwanted byproduct here, some ethane. We end up with some of our starting material reforming. We end up with a few other byproducts along the way as well, like HCl is also one of the products made. But that as a whole is our free radical substitution mechanism. Okay, I'm going to go through a second example now before I set you off on some tasks. So this time we've got bromine with ethane. Okay, so if we're reacting bromine with ethane, the aim of this process is to produce bromoethane by the end of it. So our initiation step works in exactly the same way. We start off with our halogen, in this case Br2, and UV light will allow this to split up into two bromine radicals. Okay, so these are our highly reactive species, just like the chlorine ones we just saw. Our propagation steps. First propagation step, our bromine radical collides with our alkane, and the bromine takes one of the hydrogens off this, so we end up with HBr and C2H5 radical, so this is now an ethyl radical. Our second propagation step, the ethyl radical that we just formed, now collides with a Br2 molecule. Again, some of these bromines that weren't split up to begin with will still be floating around in our reaction mixture. So the ethyl radical will collide with the Br2 and it will split those bromines up. One of them will join onto our ethyl, so C2H5. Br, and again, that's what we want to happen. That was the aim of carrying out this reaction. But then the other bromine will be floating around as a bromine radical now. So you could actually say that the bromine radicals are acting as a catalyst during these propagation steps. The bromine radicals are put in at the beginning, they cause the reaction to occur, but then another bromine radical is generated at the end of the two propagation steps. So because it speeds up the reaction but isn't used up itself, you could say it's acting as a catalyst. So this time we still have three possible termination steps. We could have a bromine reacting with another bromine to form Br2. We could have a bromine reacting with an ethyl radical to form C2H5Br. So again, that's what we want. But we could also have an ethyl radical reacting with another ethyl radical to form C4H10. So we could actually end up with butane as an unwanted byproduct in this step. Okay, right, what I'd like you to do at this point is pause your video, and I want you to have a go at these two. I want you to have a go at drawing out the full free radical substitution mechanism for bromine with methane. Do the initiation, 2 propagation and 3 termination steps. And I'd like you to have a go at the same, a chlorine and ethane free radical substitution mechanism. So again, 1 initiation step, 2 propagation steps, 3 termination steps. So pause the video, have a go yourself, and then I'll go through the answers to those in just a moment. Okay, right, let's have a look through those questions, and I'll do these in red so you can see them a bit more distinctly. So bromine with methane, our initiation step, our Br2 is going to split up into 2 lots of bromine radicals. We need UV light for that. Okay, so that's our initiation. Our propagation, our bromine radical is going to collide with our methane. And remember, in this first propagation step, the bromine radical is going to take one of the hydrogens off this. So we end up with HBr, and we end up with CH3, our methyl radical. Our methyl radical then is going to collide with a Br2 that wasn't split up to form CH3Br and regenerate our bromine radical. Okay, so again, remember, propagation steps are described as reactions that occur which prolong the life of the radical. So that there should always be 1 radical at the start of these steps and 1 radical generated at the end. Same in this second one here. Okay, the termination steps then. So this is just where we pair our radicals back up in all the different combinations. So it could be that a bromine pairs up with a bromine radical to form Br2. Of course, we don't want this one to occur because all you're doing is ending up with the starting material that we began with. We could have a bromine radical reacting with a methyl radical, and that will form CH3Br. So that's the one we do want to occur. Or we could have a CH3 radical reacting with another CH3 radical, and this time it will make the byproduct C2H6, again an unwanted byproduct. Now I probably should have mentioned at the beginning, this process, this whole reaction is completely random. So as soon as you produce your bromine radicals at the beginning, the following stages are just going to occur sort of uncontrollably. They're all just going to happen until all the radicals have paired back up again and we have no more radicals left over. So when I say we don't want this one to occur and we don't want this one to occur, but we do want this one to occur, we can't actually control it. So we just have to let the reaction happen and see what we have left over at the end. Okay, so let me go through this second example that you should have had a go at. So this time chlorine with ethane. So our initiation step, Cl2, in the presence of UV light, splits up into 2 chlorine radicals. Our propagation steps now involve ethane. So our chlorine radical is going to combine with C2H6, or not combine with it, but collide with it and form HCl, because the chlorine takes a hydrogen off this and leaves us with C2H5. Then the C2H5 that we've just generated is going to combine again, or not combine, collide again with one of the Cl2s that wasn't reacted, and it will split that Cl2 up. One of them will stick onto this, so we'll end up with C2H5Cl and a chlorine radical. And then finally, there's always 3 possible termination steps. So it could be that a chlorine radical combines with another chlorine radical to form Cl2. It could be that a chlorine radical combines with a C2H5 radical to form C2H5Cl. Again, that's the one we ideally do want to occur. Or it could be that C2H5 as a radical combines with C2H5 as a radical to form C4H10. Okay, so I'm just going to go through 3 other kind of key points that can crop up with the free radical substitution mechanism. Now you'll see here that I've already jotted down a full mechanism. It's one of the examples I went through already here with bromine reacting with ethane. So the aim of this reaction is to produce bromoethane, and we see that's one of the products of our propagation steps, and it's also one of the products of our termination steps. Now, some exam questions may ask you to write out the overall equation for the process occurring. Now that might sound quite tricky because we've actually got 6 different reaction stages going on. How do you sort of condense them down into one equation which represents the overall reaction? And the answer is you just focus on our 2 propagation steps, okay? So if you're asked to work out the overall reaction, you take the 2 propagation steps and you add them together. So you add together everything which is on the left-hand side of the arrows and everything on the right-hand side of the arrows to produce the overall equation. But you'll also spot that there'll be some things which cancel out. So for example, there's a bromine radical on the left and there's another bromine radical on the right-hand side. So I don't actually have to include those in my overall reaction. I've also got an ethyl radical on the left and an ethyl radical on the right. So they should also cancel out. So I end up with an overall reaction which involves ethane plus bromine forming HBr and bromoethane, C2H5Br. So that is the overall reaction for the full free radical substitution process. Okay, so that's one of the key points that may crop up in an exam question. The second thing that may crop up in an exam question is to do with the termination stages. Very rarely in an exam are you asked to write out all 3 terminations. So just be aware that you had to follow the instructions given in the exam paper. If the exam question says, write out the termination stage which produces the haloalkane product, you just draw out the one which makes the haloalkane product. But there have been some exam questions which have said things like, write out the termination step which results in the formation of a molecule with an empirical formula of C2H5. Well, the empirical formula, C2H5, that's the simplest ratio of atoms within a molecule. Which of these has an empirical formula of C2H5? Well, C4H10 does, that's a multiple of 2 of it. So it may be that it only wants this termination stage. So you just have to make sure you follow the instructions as to what the exam question wants when you're completing a question on free radical substitution. Okay, the final thing to mention, which is a little bit more complex, is to do with a process known as further substitution. Now, further substitution is something which we want to avoid happening. What further substitution means is we've carried out our reaction and we've made our product, and we're very happy with our product, our haloalkane. But if we've made our haloalkane product and there are still bromine radicals, or whatever halogen we're using, if there's still bromine radicals floating around, there's nothing stopping our bromine radicals from reacting with our product and turning it into another product. So in this example, one example of a further substitution step would be as follows. So C2H5Br, the product that we've already made and we're happy with, well, if this is floating around in our reaction mixture and collides with another bromine radical, essentially 2 more propagation steps could occur. So remember, in the first propagation step, our halogen radical takes a hydrogen off our alkane, so we may end up with C2H4Br radical. So it's gone from C2H5Br to C2H4Br as radical, and our bromine radical has taken hydrogen off this, so HBr. So that's a bit like our first propagation stage over here. But then this can carry on reacting. So let's say C2H4Br as a radical then collides with another bromine molecule, just like would happen in the second propagation step over here. This is going to get split up. One is going to attach onto this and one is going to float around as a radical. So C2H4Br2 and then one of those is left as a bromine radical. So hopefully you can see how these two further substitution steps are essentially equivalent to two propagation steps. It's just that rather than starting off with our alkane, we're starting off with our haloalkane. Okay, now we do not want this to occur because it just means we're going to end up with even more different products in our reaction mixture. We already know we can make bromine, bromoethane, and in this case butane. If our bromoethane reacts further, we end up with dibromoethane, so yet another product in our mix. So there is a way of reducing the chance of further substitution occurring. We can't stop further substitution, but we can just reduce the chance of it occurring. And that is to use a large excess of alkane. Okay, so if we have an excess of our alkane, if we have lots of our alkane to start off with, it maximizes the chance of all our bromine radicals being used up straight away. And if all our bromine radicals are used up in the first lot of the reaction to result in these products, hopefully there shouldn't be many or any bromine radicals left over to carry out a further substitution step. Because theoretically, if our dibromoethane was to collide with another bromine radical, we could go through a second further substitution to make tribromoethane, and then tetrabromoethane, etc., etc. So we want to stop that happening. So we always, to reduce the chance of further substitution, you just use a large excess of whichever alkane it is that you're using. Okay then, so having had a look and a listen to those different explanations that I've just gone through, you're in a position now to have a go at some of the questions from your question pack. So if you have a go at task 5, which starts on partway down page 3. So task 5, which goes from page 3 through to page 4. And then if you jump right to the back of your question pack, the very last few questions. So there are 3 past paper questions you'll be able to have a go at. So past paper question number 12, you'll be able to attempt at this stage. Past paper question number 11, you should be able to have a go at. And past paper question 10, you can also do, but don't worry about this part B here. Okay, so past paper questions 10, 11 and 12 and task 5 you can have a go at this stage. Okay.